Just give me 1 sec. Okay. It looks like it's starting recording now. Cool. Off we go. So today I want to talk about queues and decks. Interestingly spelled words. So before we get there, though, I want to talk about stacks one more time. I want to give you a good example of stacks. It's a fun idea. None of us in our lifetime have used this thing, but it's a fun example and it's historical. So I want to make what's called a RPN calculator for us, and RPN stands for reverse Polish notation. Go look it up. It's an interesting idea to want to do math in this way. Reverse Polish notation. But it has to do with stacks. Stacks are baked in. So here's the story. There used to be a very, very popular line of calculators made by HP. Like before they made computers, they made calculators, and like it was the greatest thing ever to have a calculator that you could pull out of your pocket and do math with rather than having to use like a slide rule, if you guys know what those are. So like calculators were a huge deal when they first were invented, and this was one of the firsts. And the way that you asked it to do things for you was you didn't say 2 plus 2 and hit enter. That's not how calculators worked at the start of time when they got first built. There was an implicit or explicit, I guess, stack inside of them. Instead of typing 2 plus 2 and hitting enter, you would type instead 2 enter 2 plus. And that style of typing in those commands in that way is called reverse Polish notation. So apparently there's a Polish notation. This is the opposite of that. It's the other way. So what it does is it has a stack of operands, things that you're going to do operations on, and then whenever you say an operation, it's going to pop the stack and do that thing on those operands that you have saved away. And so what that means is you do not need any parenthesis buttons on this calculator, because you can control what happens when by putting the right things in the right order onto the stack. So it's like enter pushes something, and then also the plus implicitly and pushes the other thing. So here's what happens when you say 2 enter 2 plus. So you type these keys, right? 2 and then enter, 2 and then plus. What goes on is the second you say the 2 and the enter, it pushes 2 onto its stack. Say you just turn the calculator on, the stack is empty. That's called your operand stack. This is legitimately how this worked. And then you say 2. So 2 enter, that pushes the 2 onto your operand stack. Now it has one thing on it. And then you press 2 again, and that's going to push the 2 into the next slot on your stack. And then once you type plus, it's going to, the second you say plus needs 2 things to add, it's going to go pop in the stack. That's how that calculator worked. So it goes and it pops the stack, gets the 2 out, gets the 2 out again. It knows that the second thing was like the thing below it. Like pop the first thing, that's the right side of the plus. That's the left side of the plus. It knows to do that. And then it does the operation. It calculates 4, and it pushes the answer back onto the stack. So the stack turns into 4 like that, because maybe you wanted to do more with that 4. Like now that's another operand. So it'll also show you the answer as you do that. So that's kind of how it worked. Have we ever heard of those before? Like that's a thing. Hugely popular. One of the first most popular calculators. Very expensive. So, okay, let's have an example and then we'll code it. So this is how you would turn this expression into reverse Polish notation. It would look like this. I hope you can see kind of once I show you it, how it's going to work. It's 5 times 7 times 3 divided by 8. So the 7 times 3 has to kind of happen first. I'll show you how that works. It's like the multiplication is the very first operation. That's going to be the first operation you punch in. And then it's going to do the 21, put it back on the stack, and the 5's still waiting there. So let me kind of prove that too. So here's our operand stack. You say 5, 7, 3, and like you enter in all of it. 5 enter, 7 enter, 3 enter. So your stack looks like this after you type those numbers. 5, then 7, then 3. And then you say star, and star's going to, it needs 2 things. It's going to multiply the 2 things on the top of the stack. It's going to pop the 3 and pop the 7 and compute 21 and push that back on. All right. So this is what's going to happen on the stack. Push that 21. Cool. And then you say plus, and you see how it's going to work? It's like, all right, plus needs 2 things. You just had, you got the 21 now, and the 5's underneath it. We can add the 2 things that we wanted to add. That's how you turn it into that form. No need for parentheses. The order is explicit or implicit, however you want to think about it. So all right, now we're adding. So we pop the stack. We add the things. 21 plus 5 is 26. And we push the answer back because maybe we're not done and we're not done. So that's 26 is on the stack now. I think I did that right, yeah. And then we want to divide by 8, so we got to get 8 on the stack and then divide, because it's got to push our operands before performing the operation. So we do 8 and then slash. The slash is going to give us one last pop of 2 things on the stack, and now it's going to pop the first thing, and that's the right side of the division, right? I need to remember that. And then this is the first thing in the division. It's going to pop it twice. 26 divided by 8, and it's going to push the answer back onto the stack, because maybe we're not finished, but we are this time at least. So 8, 16. Let's just do integer division. The answer is 3. Okay. And we'll push the 3 back onto the stack. It will also be displayed on the calculator as you did that. Voila. And that is how those calculators worked. And that's kind of neat, I think. So I think it would be fun to code this up, but does it make sense how to like turn this kind of into a parenthesis-less expression? It's called reverse Polish notation. It uses a stack. It's a great example of a stack, I think. All right, let's code it up. So what we will do is we will ask the user for some numbers or some operations, right? Because that's how this calculator works. Either the users type in numbers at a given time or they're typing an operation. So let's have us get those possibilities, all right? And we'll use that to modify and mess with our underlying stack of operands. So it's going to be a stack of integers, all right? So that's how that will work. We'll read a bunch of numbers or operators, and we'll ask the user, like, hey, do you want to enter a number right now, or do you want to enter an operator right now? There's a way to just like get a string and figure out if it was a digit or a character, but let's not deal with that. Let's just ask the user first, or Q to quit. And then, yeah, every time we read a number, we'll push it onto our operand stack. And every time we read an operator, like a plus sign or a division, we will pop our stack twice, because every operation that we're going to implement needs 2 things, 2 sides to every plus and minus and whatever. And we'll perform our operation on those 2 things, remembering to take care that the thing underneath is the left side. Like the thing on top is the right side of the operation, because like subtraction and division, the order matters. And we'll deal with that. And then it's always push the result back on the operand stack. And yeah, once you're done, if you did it right, if you did a valid expression that like computes one answer, you should have 1 thing left on your stack at the end. Otherwise, you messed up. All right, and so that's what should be displayed to the user. That's your answer that you give back to them. So that's kind of the algorithm. And are you ready to see it in code? Let's do it. Very exciting. So we'll call it rpn.cdp. And so I'll need stack stuff. And I need a stack of ints. That's my operand stack. That's what I'll call it. And here, let me move my computer closer to me. There. And then just like forever, until the end of time, until the user types Q, I want the user to give me what they want to do right now. Do you want to give me a number? Do you want to do an operation? Do you want to quit? So that's my idea. Enter N to type a number. O for an operator. We'll just have them type a character to say what they want. You could get fancier here, though. Or Q to quit. And that's just the fastest way to do this. So I'm getting a character first from the user. And that's going to dictate what they want done. So if that number, if C was N for a number, then I do something else. If it was O for an operator, we'll do something. Let's just say else, assuming they didn't do anything else right. Like they could have said Q or they messed something up. So let's assume it. Assume they wanted to quit if they typed anything else. Assume it was Q. And so we have to say what happened. So, okay, if the user typed a number, all we got to do is push it to the stack. Like that's what it means to type a number. Get it ready for the next operation. So that's just going to be, well, we need the number now. So we'll say, call it N maybe. And we'll say cout. All right, you said you wanted to type a number, enter that number. Enter the number into N. and then our stack is called operand stack. So let's fill it. Now we're going to push it. So that's the main job of us right now. Operand stack.push that value n that we just received. All right, so that's what happens if the user gives us a number. That's just how that works. And operator, that's more complicated, right? If we get an operator, then we have to start popping our stack. So does it make enough sense so far, though? All right, just shout out if it does not, or it stops making sense. So if they want an operator, then we need to get the operator, like char, call it O. Let's say cout, enter that operator, please. Enter the operator, we'll get it into O, and then we're going to do plus, minus, times, and divide. So it's always two things. We're always going to do two things. So it's always, you say plus, for example, we're going to pop the stack twice, and it's always the thing on top is the right side of the operation. That was the right side, the thing underneath, because there's always two things. The thing lower down will be the left side, because you would have typed that number first into the stack. Okay? So we're going to pop our stack twice. We need to get the two operands off the stack. You can imagine that the user might mess up here, like they say plus after they only typed one number, then it's going to have a runtime error because the stack cannot be popped twice. So you could be checking for that, but I'm going to be lazy. Assume the user did the right thing. So int, the first number I get when I say operand stack.top is going to be the second thing. So I'll call it n2. That's operand stack. Give me the top thing, please. The thing that's on top right now, that's the second operand. Second operand is higher on the stack than the first. That's how that works. And then that means the thing underneath it then is going to be the first thing, the thing on the left side, the first operand to this operation. So in order to get access to it, I have to pop it. So operand stack dot pop. That's how the C++ stacks work. So I got to pop that stack, and then I can get the other thing. And that will be my N1 now. And again, I want to pop the stack. I'm using that. I'm eating up that number and producing another number from it. So now I have my N1 and my N2. I've got an O for an operator. I just need to turn that character for the operation into an actual like computational effect. So, all right, depending on what O was, if O is equal to a plus, then that means we want to do addition on N1 and N2, like N1 plus N2 is our operation, and that's our result, and we'd like to push its answer back to the operand stack. Operand stack dot push that value. All right, that's what goes on, and it's exactly the same for everybody else, right? Else if O is equal to a minus, then we push subtraction of N1 and N2, right? So that's that one. Same for multiplication. We push the multiplication of the two things. And then let's just say else, the only other one that we're going to support is division. Let's just pretend that was the only other option, division. All right, so we'll push the result of dividing N1 by N2. And that, I think, is all that we need to do for our operator version of things. So if the user wants to type an operator, we need to actually perform that operation after they give us which operator they want to use and push the final answer back onto the stack, just like this drawing. Does that make enough sense? You see it? This is an interesting, more complicated example of stacks, I think. And then finally, if the user said, hey, I don't want to type a number or an operator, just like I'm done, that should break us out of this infinite loop, like we're finally finished. They want the answer now. So once I'm out of this loop, there should be then one thing left on the stack, and that is the final answer that they wanted to be displayed on the calculator screen. So that's what we want to do right here. So display the answer after the user typed Q. Is there anything I wanted to say? Like this process right here is perform the operation O, whatever that was. Okay. Display the answer after the user type Q. It'll be on the top of the stack. For example, it's on the top of the stack. And so that's our result. See how it's, all right, the final result is whatever is on the top of the operand stack. And yeah, you could make this as fancy as you want, like optionally. Maybe there isn't something on the top of the stack right now. Like you could throw an error if the stack, throw an exception if the stack has more than one thing on it or is empty. Because that would mean like you're not finished yet. You messed something up. There's a button to clear out the stack, I assume, on that calculator then. So yeah, that's kind of how that's going to work. And let's see it happen. Let's do 2 plus 2 and then the fancier one. But is there any questions about the program before I run it? Are there any questions? You see the process? It's kind of neat. Sorry I can't show it all to you at once, but you'll get it all later. So all right, let's do 2 plus 2. So that's going to be 2 enter 2 plus. So 2 numbers, right? N2, another number, N2. So we got 2 plus 2 and 2 on the stack, and then operator plus, and then Q to quit. Hey, the result's 4. Nice. I like it. And then we'll do the fancier one. We're going to do 5 plus 7 times 3 divided by 8. So it's 573 times plus 8 slash. All right. So 3 numbers, 5, 7, 3, and 5, and 7, and 3. And then 2 operators, O star, O plus, and then 8, number, and 8. And then one last operation, O division. Q to quit. Cool, we get our 3. Look at it go. So yeah, that's how that worked. And now if you ever become a collector of these kinds of calculators, you know how to use them. And I think that's all that I wanted to say. Any last questions about this program? Just a neat little example of stacks. They pop up. And so now you know more. Good practice. So yeah, if we're good with those, I would like to actually talk about the main topics of these sets of slides. So we can talk about queues and decks now. That's how you pronounce it. It's kind of weird. Queue is a word that we know, but deck is kind of a word created from the word queue. So like, it's all very French sounding. So all right, let's talk about queues. It is kind of, in a sense, the opposite of a stack. It's very similar to a stack. They're always taught together, stacks and queues, stacks and queues. It works ever so slightly differently to a stack when you implement it deep down, because it'll still use a linked list, and that makes all the difference. All right. So the metaphor is it's legitimately a queue, because you know that British people, they use that word to mean line. So think about a bunch of British people waiting in line at a checkout stand or something. So what a queue looks like is, this is how I'll draw it. There's a concept of the front of the queue, like the person who's at the checkout stand right now, and then the people waiting behind. So there's a front and the back of the queue, all right? And you can put any kind of data inside of it, just like numbers. You make a queue of ints just like we made a stack of ints. So that's kind of what it looks like. There's a front, there's a back, and here are some very familiar sounding operations that you can do on queue ADTs. So here's how you define a queue in terms of its operations. You can push to a queue, you can pop from it. You can get the front, that's the main difference in terms of naming from a stack, because a stack would be top right here or something. And then check and see if it was empty. Those are the things that you would do. And the place that you push and pop from is different. For a stack, it's the same. For a queue, it's different. For a stack, it's always you're dealing with the top. You're pushing and popping to the top, or from the top. And for a queue, you do one thing to one side, one thing to the other. So for a queue, when you push, you're pushing to the back, like a new person coming and waiting in the line, waiting in the queue. And then when you pop from the front, like that person just got, they just finished buying all their stuff. So here is an empty queue. It's got nothing in it. It's got a front and a back, though, still. And if we push 1 to this empty queue, it's going to go to the end, but it's going to become the first thing, of course. So the front and the back look like that. If you push 2, here's what it looks like, right? You got 1 still waiting there, and then 2, you push to the end, front and back. Some people call it like front and rear. You'll hear that in some textbooks, but I'll say front and back. You push 3. It'll be 1, 2, 3, of course. Front and back. And then the difference now from a stack is what happens when you pop. When you pop, it's not going to take away the last thing you put on. It's going to take away the first thing that was waiting ever so patiently at the start of the line to be serviced. So it's going to turn into 2, 3, and that's the main difference from stacks. Okay? It was the one that was waiting. The first thing that you pushed is going to be the first thing when you pop. All right? That's how it goes away. And then the second thing, like if you were to pop again, it's the 2 that's coming out. You're getting that off. 2. So that's how that works. So when you pop, you always remove from the front. When you push, you add to the back. Okay? And so instead of calling the thing top, the place that you can access in the queue is always the front thing. Everybody else has to wait. Okay? It's not the top anymore, it's the front. And of course, you can still check for emptiness. So yeah, are there any questions about that? What it would mean to be a queue? You kind of see what it looks like? All right. So, what else do I want to do? Yeah, I think I have a question for you then. If you can kind of see what's going to go on. Here's my silly drawing of what it means to be a queue. You're adding stuff. You're getting rid of stuff. You better believe you can use a linked list to do all this. Hey, there's my drawing, very small. I have a question for you. Right? Say that we're going to implement, because you can, say that you're going to use a linked list to implement this idea of a queue. All right. So I want you to discuss with the people sitting next to you. Please say hello. Talk about your weekends for a second, and then come back here. Make sure to do attendance too. I'll stop that when I remember next time. But let's have a few rapid fire by clicker questions. I'll get us ready for the first one. So please discuss all 3 and enter in the first one. But I'd like you to think about what are the worst case big O running times. When you say big O, I mean big theta. What's the tightest bound rate? For pushing to a queue if you're going to implement it using a linked list, popping from a queue if you're going to use a linked list to do it, and then accessing the front value, the front element value. All right. So see if you can figure that out. Say you've got a queue and you're going to use a list to do it. So this will turn into like the list 1, 2, 3 or something. Trying to draw it, think about it in your mind. Is it going to be constant, logarithmic, O of n, linear, where n is the number of elements in the list right now, the number of things in the queue right now, because that'll be equivalent. Or maybe something else. Maybe I'm trying to trick you a little bit. So try to come up with your answers for push, pop, and front, but please enter in just your answer for push right now. Okay? So questions about the question? See if you can figure out what it's going to look like, and we'll go from there. And we'll just come back and do them all in order. And you can implement it however you want with a list. Like, do you want to push to the front, push to the back? Do you know exactly both ends of the list? That would take me to do and I'm making that scale. I'm pretty sure that's about the same. Yep. So you have to remember your list running time stuff. Yeah. That should be too short if it's not already.
You also have to very well
That's hilarious. That's my timer. Take another few seconds to decide on stuff, and then please enter in your answer for push. All right, we ready to discuss? Let's come back. Let's see what we're thinking. If you need a few more seconds to enter it in, let me do one thing and kind of draw what would happen. Like, it kind of depends on where you put things in the list. But like, say you wanted to represent 1, 2, 3, the Q 1, 2, 3, with the front and the end. Depends on which side you push, but one way to represent that as a list would be the list: 1, then 2, then 3. You could have pushed back every time you pushed to your Q. That's one way to do it. Is that the best way? We will discover. We'll figure that out. But there's your front, there's your back. And that's kind of how you can think about your Q deep down as like concrete data structure stuff. But let's see what we're thinking for push. Look at us, we think it's constant. Nice. That is correct. We'll talk about that in a second, but let's do just rapid fire. What do you guys think for pop? And then we'll do front as well, and then we'll see if there's a pattern. We'll see if we're all happy about it. But 3 more seconds to get your answer, and I assume you're on the page already. Let's see what we're thinking. We also think A, we're the alarming majority. Beautiful. Everybody agrees. One last one. Front. To get the front element. Is that harder than any of these other things? Dun, dun, dun. So let's figure this out. Nice. So some of us think it might be linear, that one. So let's take a look at this. So it is, in fact, constant for everybody. All right, make sure we've done attendance. I will stop that in a second. But, oh man, it is going to be constant. So that's good. It's good that we thought about all those things. It does get a little tricky with pop, because there is a way, A will be the right answer. There is a way, right, to make it linear if you did it backwards. Because you know that you could have turned this Q into 1, 2, 3 the list, or 3, 2, 1 the list, couldn't you have? Because you could have totally pushed front instead of pushed back every time you push to your Q. You have those 2 options as a list, right? That's 2 easy things. Pushing is always constant, but popping is not. So if you were to do it this way, if you were to represent your Q like this, it's just a representation, right? You could still get the last thing very easily. Still, like, the front would be the end of your list. You can go there, you have a pointer there. That's your last pointer. Get the value, that's easy. But to pop, that's hard because you need the second to last element, right? So it's better to do it this way, where you push back to your list means that's how you push to the Q. All right, that's how you'd represent that idea. Does that make sense? You see how it could have been worse. It could have been linear, but if you're thinking it and doing it right, it is going to be constant for all 3, because to pop from this kind of list where the front thing is the first thing, that's an easy process. Question?
But if it's a doubly linked list, it wouldn't matter, right?
If it's a doubly linked list, it does not matter at all. Yeah. If it's a doubly linked list, you can move around and get to the second last thing just as easily as you can get to the second thing. because it's kind of that idea. Good. Other questions? So it's going to be constant. If you have a problem that could be solved using a queue, like, I don't know, you're programming people waiting in line for something, like, you have some very fast, like, ways to implement these ideas. So that's great. Yeah, let's analyze. So yeah, like stacks, a list is a good representation because it's only like the top, the front, the back. Those are the only places you're really accessing. You can do those kinds of things in constant time with lists, which is beautiful. All right. So yeah, the empty queue then would be the empty list. So that would correspond to, like, in Python land, it's like it's nullness, right? It's the idea of nothing at all. So it looks like in Python, like the null pointer would be our front and back for an empty list, and then push would end up being push back for our singly linked lists. And so, like, the queue with just one in it, well, that's just the node one, not the one and only thing in that list. You push again, you're adding to the back of your list. So it looks exactly like we're drawing the queue, so that's perfect. One, then two. That's how that would look. And then pop, if we were to pop our queue from here, we were to pop that, we turn it into the queue with just two in it, because the one's the thing at the front. The front thing goes away when you pop. And as we're getting rid of this node, which is constant time, since it's at the front for our singly linked lists. That's beautiful. So that turns into just the list, two, and that's it. Okay, so pop is pop front. Front, just the idea of getting the front thing, is if we're pushing back and the front is at the front of our actual list, that's getting the first element. It's going to your first pointer, getting the data out, right? That's how you do it, just like a dereference and a dot or an arrow operation that does both at the same time. And then just like if you want to do the empty operation, right? See if your queue is empty or not. That just checks and sees, right? There's a way we represented our empty queue as an empty list, and we know what it means to be an empty list. It's like your first and your last are null. Okay, so it's a check against. You can just check one of them, like check if front is null, because like you know that they'll always correspond in that way. So that's again constant time. So it's constant time for every darn thing you could want to do to a queue. That's beautiful. So if you find a problem that could be solved with a queue, you are in good shape. Can't do any better. Any questions about that? The implementation, the analysis? Yeah. So I'm not even going to write code. I think it's pretty clear. I believe that you could do it. You remember how I said that stacks are LIFO, L-I-F-O? The last thing in is the first thing out. That's an acronym that you want to remember. Queues are FIFO. People say those things. So queues are the opposite of stacks. They are FIFO. They're the first thing in is the first thing out. The first thing that you put in is going to be the first thing that you get out when you pop. So the first thing you put in with your push, like you push one, then you push two, and then you pop, it's the one coming out. The first thing, queues are FIFO. They are getting the first thing out. The first thing in becomes the first thing that you're getting out. That's how I want to say it. All right. The opposite of that is stacks, LIFO, where it's the last thing in is the first thing out. So like you push one and you push two and then you pop, you're getting the two off with the stack, right? The last thing that got into it was the first thing that's coming out of it. And that's the main difference between queues and stacks. And they solve different problems. All right. Any questions about the difference? Do you see it? They're pretty simple data structures. It's not the world's hardest thing, which is a nice thing to have after a test. So what else do we want to do? That's a thing. So just for fun, I think that would be fun. So, okay. There is a queue in C++ standard template library land. Let us look at the documentation in a British way. Jolly good. So let's finish with just doing that. Okay. So we'll talk about queue stuff now. FIFO queue, beautiful. It's got all these things and looks very similar. You got push, you got pop, you got front. They even let you access the back for this kind of queue, but we're not usually going to do that. That's not what everybody agrees on. Empty, and then size. Apparently we get the size as well, which you could have kept track of in a member variable, adding one when you push, subtracting one when you pop, something like that. Or you can iterate through your list to make it linear time, but that's a thing. All right, so a great example of a queue is the word queue in music land, right? You have like Spotify queues, Apple Music queues, whatever you listen to your music with. And you know what that means, right? You've got like the current song at the front of your queue is the one playing right now. Like you push song A, there's your queue, you're playing that right now. But like, oh, you know what? That reminds me of song B. I'm going to add it to my queue. So you've been pushing to a queue data structure that's in your music listening app, whatever one you use. You're like, oh, that reminds me of song C and song D and song E. And that's exactly what you would expect, right? Once you're finished listening to song A, it pops the queue and remembers that B is the next thing. That's exactly what's going on. It is a queue data structure. That is one way that you can implement it legitimately. And that could be why it's called that, potentially. So yeah, that's how that works. And yeah, you'll always be able to get the next thing in your queue after you pop it, and then get the new front. That's how you can see things. So kind of here's how you can think about implementing that. Maybe this is what they did in Spotify. A queue not of integers or of strings. It's a queue of whatever the song data type is that they represent. The idea of a piece of music that you could listen to wherever it is, somewhere in the cloud. And then like you push song A and it starts playing because your queue is empty. And then eventually you want to like pop your queue, get the new front, and start playing that in a new way. Something like that. I don't know. Yeah, so that's the idea. And I hope you see that this is a great example of it, right? That's how that could have worked. So I think that's pretty much what I wanted to say. Like, it's a real life example. You've all used queues, okay? And then we do have time. It's just going to be a short lecture for the day. Let me show you one thing that I will never test you on. It's just a very interesting thought experiment. You can make a queue out of stacks. You need two of them, but you can make a queue out of stacks. So just to show you that, like, an ADT legitimately means ADT. You could implement these things however you really wanted to. You could use just one big long string. You could use an array. You could use a vector to implement a queue if you really wanted to. You can use two stacks. This is the silliest thing that you could possibly want to do. It is very inefficient, but it will work. And so let me show this to you. It's just a very classic example, and we have plenty of time to do it. All right. The idea is we need two of them because you know that if I push stuff to a stack, I'm getting it off in reverse order. But if I popped from that one stack and had a second stack laying around, it now would be in the correct order, wouldn't it? It would do the reversal for me. And so that's kind of the secret there. All right. So it's just a very classic example. We'll analyze it as well. It's fun. All right. I will never try to give you this on an exam. That's too much. So yeah, the moral of this story, just like think about this in the back of your mind as I'm explaining it. We need two stacks so that we can reverse things and get them in the right order as from a queue's perspective. So we can reverse. So here's the idea. So yeah, there's going to be two stacks, and here's kind of the operations. There's stack S1 and stack S2. S2. And okay, when you push to your stack, or sorry, this is a queue we're talking about. We're trying to implement a queue using two stacks. So when we push to our queue, what that means is we push to our stack S1. That's how that will correspond. All right. This is a silly, interesting thought experiment, and we'll code it up in a second. So let me just draw what happens. When you push 3, every time you push to your queue, it's going to push to the stack S1. So like 3 is going here. I'll push 2, it's going to do the same thing. It's going to push to S1, then 2, right? And then I want to get the front of my queue, which is 3, right? It's meant to, like, I push 3 and then 2, so this is what the queue looks like right now. Just like that. If I want the front, I need the 2 out, or sorry, excuse me. If I want the front, I need the 3 out. There it is at the front there. And it's sitting down here. I can't get it just yet, but that's why I have a second stack, all right? So if you want to do front or even pop, the idea is that S2 will be in the correct order. If there's something in S2, get the top of it right now. Like that's the front of your queue. But if there is nothing there, like there isn't right now, then pop everything out of S1 and push it all in that order to S2. Then you have something at the top that you can pop. And watch what's going to happen. It's like, all right, I will pop the 2, push the 2. I will pop the 3, push the 3 to S2, and look what I can get out of that stack now. Now this is empty. I can get my 3. All right, I can get my 3. And so now I can get the top of S2, which is the 3. That is the front that I wanted. Does that make sense? See how that's working? So you can implement, legitimately, you can implement a queue using 2 stacks. And then pop is going to be very similar to front because it's going to deal with this side, the stack here. So it's going to pop from S2 if S2 has anything in it. But if there's nothing there, then it's going to move everything over to get it in the right order for popping from a queue's perspective. All right, so we're going to pop that 3 by getting rid of that. And that means our queue is just the queue with 2 in it now. Yes, in that order. And then I'll push 1 to my queue, which means always push to S1. Boop. And then I would like to pop. So the first pop is always going to all right, if I can pop from S2, pop it. And I can. So I'll get rid of S2, its top thing. So I'll pop that thing off right there. The 2's going away. Get the 2 off. Oh, sorry, the queue right now is looking like this, right? Let me draw just like the original as well. So we had 3 and then 2, we popped the 3. Now we have just 2, we added the 1. So the queue looks like this, and we're about to pop the 2 off, which involves popping from S2, and we can. So that's gone. And then if we pop it one last time, well, now there's nothing in S2 anymore. There's nothing there. And so our algorithm, the way that you got to do this is we have to bring everything from S1 over, put it there. All right, that'll get in the right order. So pop all of S1 and push in that popped order to S2. There's just one thing though. And now we got the 1 sitting there in the right spot, and we're ready to pop it. And so we got that happens, and now our queue is empty. All right. And if you ever want to check if your queue is empty, it just means that there's nothing anywhere. And so you go and look in both of your stacks, because depending on what operations you've done, things may have moved over from one to the other. So just make sure there's nothing in either of the stacks. That means your queue was empty. Does that make sense in picture form? This is weird. You would never want to do it this way. It's silly, but it's a great example. All right. And so let's code that up. We have plenty of time. A queue using 2 stacks. I love it. There we go. Queue using stacks. So I'm going to include stack, queue. It's going to be great. And yeah, let's see. This is the class. I'll call it queue using stacks. And then I'm going to have some operations and some member variables. My 2 member variables will be the 2 underlying stacks that I'm using to represent the queue. So it's going to be stack of ints S1, stack of ints S2, and then here are my public operations, push, pop, front, and empty. So it'll be a stack of ints, or sorry, a queue of ints. So if we push, that's void push. We're going to push some new value that's an integer. We'll deal with that in a second. And I'm just going to be lazy and implement it all within the class. It's faster that way. And then we're going to have pop, just does something, it's void. We're going to have front, which is going to give back the thing at the front of our queue, which is an int, just a copy of it. And then empty checks and sees if our queue is empty, and that's a bool value that we get back from that one, right? So those are the things I want the user to be able to do. And so here's my silly example. This one, 3, 2, front, pop, push 1, pop, pop. Let's do that. Queue using stacks. Call it, I like to call my queues little q. Queue.push 3, push 2. Get the front. We'll see out it, I guess. Queue.front. That should be the 3, right? And then we will pop our queue. And then we push 1, pop, pop. All right. Queue.push 1. And then we popped twice. And just for fun, let's just do the look at the front as we pop it so we can see it changing. All right. And then after that's finished, we should also have an empty queue now. So checking emptiness should show that it is, yes, true, empty now. That's how it should work. I hope you can kind of imagine what's going to be printed here. This will be true at the very end because we've popped everything. And now we can implement this. So, okay. To push something to our queue using 2 stacks, we push to S1. That's S1 dot push that value. because that's our member variable's name, stack events S1. To pop from our queue, that's more complicated. So it's like, can we pop? It's from S2 if we can. If there's nothing there, we got to take everything off of S1 and move it over in the popped order into S2. So this is a great example of iterating through a stack as well. So, okay, if, let's see, if S2 is empty, we're kind of in bad shape. But if it's not empty, we can take something, right? We just want to like, we want to do this, S2.pop if we can, but maybe we can't. So like if S2 is empty, if that's true, right? Or I can just say this, if S2.empty, that gives back true, then I'll make a little helper method for myself that'll be private, the user can't do it, but let's call it move S1 into S2. I'll just call that on myself. I think that will be useful. That can be a little private method that's a helper for me. Void move S1 into S2. And what that will do is this entire process, like pop everything from S1, push it to S2, and then I'm ready, in theory. So that's just like, all right, as long as I have something in S1, go get it, push it onto S2, keep popping as long as there's something there. So while S1.empty is not true, while it's not empty, while there's something still in S1 sitting there, then I want to pop from S1. I know there's something in there if I can still run the body, and push to S2. That'll be interesting. All right, so we want to push to S2 whatever's at the top of S1. Oh goodness, what have I just done? There. Push to S2 whatever's at the top of S1, and then we've just done and used up that thing in S1, pop it down. Okay, does that process make sense? Until S1's empty, do that. That'll get everything off, move it on to where it needs to be over here. Cool. And that's pretty much that algorithm. There's that one. So in theory, this is move something there. Like the user should not be calling pop if there's nothing to pop. We'll just let it fail. But that's how that one works. And then front's pretty much exactly the same. It's like get something. It's the top of S2 if there's something there. If it's not there, move stuff over. So it's pretty much all this over again, but it's going to return S2.top, whatever's there. It's going to return a thing now. And then finally, checking for emptiness is, depending on how you've done it, like you just push things only, like then everything's sitting on S1. If you've done any popping at all, if the last thing you did was a pop, everything might be over on S2. So like it depends. All of your elements are either in S1 or S2 right now. There might be some shared, or nothing shared, but there might be some split between the two. It's like there is an element in your queue if there's something in either of the stacks. And so empty is true if both stacks are empty. So return back, hey, whether S1 is empty and then also S2 is empty. If that's true, the whole queue is empty. Otherwise, if any one of those is not true, the whole thing becomes false. It's not empty. There's something in one of them, which means there's something in that queue. Okay? I think that is how I want to explain it. Are there any questions about how this is going to work? You see how it corresponds to the pictures? It's very, very funny. I think it's cool. It's a great thought experiment. So it's going to work, assuming I didn't do anything silly. We really will get we pushed in that order, 3, 2, 1. We're going to get it off in that order because that's how it means, that's what it means to use a queue, to be a queue. So what do you know? We say 3, 2, 1, and then this last one means true. Empty, yes, it was empty. Cool. Look at us. So yeah, we've seen it work. That's those operations running. This is how we're implementing them. I'll give you all this code. Any questions yet? Now that we've seen it in action. Because the last thing I want to do is analyze it, because that's our job as CSCI 41 students. Let's see, like, we know that the best way to implement a queue would be using linked lists, and that would be constant time for everything. Let's see what would happen here. All right. So here, if we push to S1, stack push is constant. So we turned it still into a constant time thing. So push to our queue, even though it's made up of 2 stacks, is still constant. That's nice. And now we got to think about the other. Empty. Empty is also easy, right? Empty is checking and seeing if both of our stacks are empty. And if they're represented by lists, we can just check the first pointers, see if they're null. Those are still constant time things that we could do. So it's constant to check for emptiness, constant to check for if our stack is... constant to do pushing and constant to check for emptiness. Questions about that? You see it? So we're implementing stacks using linked lists in the best way possible. We get those things. And then pop in front, worst case, you've pushed everything and then you do one pop, right? Like these are your stacks. You push the 3, then the 2, then the 1, then you say pop. You better iterate through all of this, right? Push it here and then get something off. Does that make sense? So that's going to be linear time in terms of how big everything is, because it's going to be a bunch of pops and pushes, which for themselves are constant. But in the worst case, you got to bring everything over from S2 that you've pushed onto your queue right now. Like all n things are coming to S2 and being pushed, and then we're getting rid of stuff. Or yeah, if it's a pop, then we're getting rid of the top thing on S2. So it's a bunch of constant time things, but in the worst case, it's linear number of constant time things. Oh yes, very important. Zibo. Does that make sense to us? So that's how it's gonna be a linear time thing, even though it's just a bunch of constant time stuff together. All right, it's this is the culprit, our move S1 into S2 stuff right here for pop and for front for the same exact reason. Like popping and getting the top, like those are the same, right? Those are constant time operations still. But that's our bottleneck. In the worst case, we got to move everything over, all n things, and so it's O of n for both of those operations in the worst case. Does that make sense to us? So a fun thing I get to tell you right now is one day, like there's more to this, one day when you get to like an algorithms class at a 4-year college, you'll discover that this is not the full story. Just like I kind of told you, if you remember me saying that pushing to the back of a vector is in the worst case linear because you have to resize, right? Remember me saying all that? But at the same time, it's not, because you're not going to do it too often. Remember those words? So on average, or sorry, not on average, just like over time, pushing back to a vector is constant. Even though sometimes you're spending linear energy to resize and move stuff over, it still ends up being constant if you account for that in a certain way. The same is going on here. If you think of this in terms of the life of your data structure, like I'm pushing things and then I'm popping things, you are still like pop in front, they are over the life of your data structure constant. And the reason that's true, the reason you can argue that, and the reason that is the thing, is that think about every individual element that you could ever want to push onto these stacks, like 3, 2, 1. You're putting it here, and you're moving it there. Think about, like, zoom in on one element. What's going to happen to that one element? It's eventually going to get popped and pushed, and then maybe popped again. Those are all constant time things. Does that make sense? So from each element's point of view, it's having constant things done to it. So if you have n things and you're doing n operations, it's very hard to explain. It's called amortized analysis. It's like it's technically constant. Because in the worst case, right, you have to move everything over, but then it's going to be constant from then onwards, right? So you do have to pay a price to move stuff over, but it's only ever going to happen once. And so if you try to divide by all the operations you're ever going to want to do, your n operations, like it averages out to constant time. That's what I'm trying to say, which is very complicated. It's a fancier thing that you'll study one day. For the same reason that vector pushback is amortized constant time, so is pop in front for these stacks, or for this queue made of stacks. That is something you can look up. It's called amortized analysis. Yes?
So if over a larger sort of data span, it's going to be constant time, would we describe the function as constant time, or would we describe it as linear?
In this class, I want you to say linear. Okay? Do the analysis that I've taught you, but once you get to a more complicated algorithms class, then we go look at vector. You're gonna start saying those words. So push back. Boop. This is always a complexity. Complexity is technically constant for pushback on a vector. It says amortized time. Reallocation may happen. So it's taking that into consideration. Reallocation itself is up to linear in the entire size. Like that's the full story. Okay, and that's what you'll learn to say when you're analyzing algorithms. But in this class, I just want you to think about the worst possible case. Okay, that's the analysis we're learning how to do. Great question, though. Other questions? This is philosophical in a sense. All right, there's two different lenses through which you could think about the data structure, like throughout its entire life, or I'm performing one operation right now. How bad could it be? That's what we care about right now. Let's zoom in this class at least. Okay, we don't have to zoom out too much because that is a little more complicated. So yeah, any last other questions about this or anything else? Because that is, for the slides at least, that's where I want to stop. I do have one last example because we do have plenty of time today. I just want to show you another example of shadowing member variables because I keep seeing it. And apparently I gave that example during this lecture last semester. Like I'll just keep showing it to you until it sinks in, because it is a very hard thing. It's very subtle when things go wrong with it. So if you shadow your member variables, you're going to have a bad time. Let me just show you what that means again. Shadowing member bars.cpp. Oops, of course I spelled that wrong. Shadowing member bars.cpp. Dun, dun, dun. So here, let me do something weird. Class C. What it will do, what this class is going to have, it's going to have one member variable called x, and it's going to have some windows into that x value. It's going to have a getter and a setter. Int get x and void set x to a new value, new x. This getter could be const. I'm just not going to play that game right now. That's not the problem. Dun, dun, dun. What do I want to do? So yeah, the getter, I guess we can do it right. Get x const. Why not? Returns x, of course. That's your member variable. And then set x, I'm going to do wrong. I'm going to say int x equals new x. Do we see the problem? You remember me talking about this before? Because this is a very common error. Where it just happens. It's very, very easy to do. Okay, so we've just lost our member variable x when we did this. Okay, so this line, remember what happens when you do this line. Every time you say a type name, that makes a brand new variable. This creates a new local variable called x that shadows the x member variable. All right, and so that means for the duration of this call, there's a brand new thing called x. Has nothing to do with this member variable called x that we really wanted to set, and that's what's getting set, but that effect is going away because it's just a local variable to the set x method. Does all those words come back to us? Does that make sense what's going to go wrong here? Like this will not work. All right, so let me show that to you. I'll make a C object called little c, and I'll say set x to 42, but we know that 42 is not getting to our member variable x. All right, that's what's going to go on. And now if we were to say c.getX and print that, we have no control over anything. Oh goodness, did I not say anything right? GetX. Oh, excuse me. This is C's stuff. C's getX. See? Very easy to make these mistakes. C's getX, C's set x. Now you should be happy. And we get this random number. All right, we get that random number. If I rerun it, I'll get a different random number. Great. Lovely. What the problem was is that we made a new member variable. We should have just been talking about the one we already had, right? Just like for the getter, it's like I'm not declaring a new x. Like I have an x. I have it. It's my member variable, and I want to use that one, right? And so the correct way to have done this would be this. Correct way to do it is just talk about the thing you already have. X equals new x. Don't say int x. Just my x. My x member variable, it already exists. It's part of me. It's part of the C object that I'm working on right now. That's how it gets set properly. Okay? So yeah, just remember that when you say a type name, that makes a brand new variable. That will make a local variable in this case, which is not what we want, because then we have shadowed over this one. The new one takes precedence, and we're not able to access this anymore. Okay? So yeah, we get some random weird values, and it's very, very hard to track it down. I think you can imagine. I'm sure you've experienced it already. So I just want to get that into your brain another time so that in theory you'll have a new place that you can go looking. When you see weird things happening, go and check for this, because that could be the culprit. Okay? Questions about this example? Do you see it? That's very, very important. It's a very, very common error, though. So it's worth hitting hard a few times. And I think with that, that's all that I wanted to talk about for the day. So are we good? Any last questions about any of this stuff? Now that's had time to sink into your brain. So yeah, that's all that I've got. I will give you all the stuff as usual, and no new assignments this week.